Continuing on our Cisco segment routing innovations for iOS XR 7.3.1, we will move to the next topic, which is segment routing performance monitoring. Performance monitoring is an important area of innovations at Cisco, where we can not only provide the ability of the operator to build the services and the transport they want, but also to be able to monitor it. In this section, we're going to cover 3 key innovations in iOS XR 7.3.1. The first one is what we call name profiles. A name profile is a template where the operator can customize the configuration parameters for segment routing PM operations. This will allow you as well to share configuration parameters between or among segment routing PM operations. For example, you could have a PM probe running on a link on, let's say, a given interface, interface 0. That interface will be associated with a delay profile. And in the delay profile, we're going to have the parameters that will apply to that SRPM operation. Likewise, I could have a segment routing policy in Violet. The segment routing policy is also being run a PM probe over it, associated with a delay profile, for example, where I configure my parameters. In iOS XR, we support different types of profiles for SRPM. The so-called default profile, it will apply to all PM operations which are not associated with a particular name profile. On the other hand, a name profile will apply to specific operations which are assigned to that given profile. And obviously, it will override the default profile if it's applied. There are 3 main types of SRPM profile types that are supported. A delay profile, which is applicable to interfaces anytime you run a delay measurement operation on a link. You also have a delay profile that is of type SR policy, which apply when you want to run SRPM operations that measure delay over a segment routing policy. And you also have a liveness profile that is applicable to segment routing policies when you run liveness detection over an SR policy. If you look at an example, here we can see name profiles when they are applied to link operations. In particular, we have a delay profile applicable for interfaces for default parameters. You can have all the parameters that will apply to the default link delay profile. On the other hand, you can also configure a named link delay profile where you may have also different parameters configured. When we look at the interfaces, interface Gigi 0000 is just being configured for delay measurement, and without specifying a delay profile, the parameters of the default link delay profile will apply. On the other hand, Gigi 001, which has a delay measurement enabled and a named delay profile applied, then the parameters of the named link delay profile will apply to the operations on Gigi 0001. Likewise, we can also have a segment routing policy delay profile, and it has also a default SR policy delay profile or a named SR policy delay profile. This time, the application of the delay profile will happen underneath the policy. So in this particular view, we have a segment routing policy foo, where we enable performance measurement, and when we just enable delay measurement underneath without specifying the delay profile name, therefore the SR policy foo will use the default SR policy delay profile. On the other hand, policy va is enabled for PM and delay measurement, and it has the reference to the name delay profile, and then that is the profile that is going to apply for policy va. Lastly, we have a name profile for liveness monitoring under an SR policy. So we have a default SR policy liveness profile, or we have a named SR policy liveness profile. And like before, we could apply a liveness profile underneath the policy or not. If we don't, then we will apply the parameters under the default SR policy liveness profile. That will be for policy foo. Or if one is applied, like in policy va, then the name profile configuration will apply to it. Now we move on to our second topic for SR performance monitoring, which is SR policy delay measurement with loopback mode. This is a very important innovation that allows the operator to be able to measure end-to-end delay over an SR policy without any dependency on the endpoint of the policy. It's going to bring a lot of simplicity, and by removing the endpoint dependency, we are just sending probes from the head end to the endpoint, and the endpoint is simply sending them back to the head end. There is no hardware timestamping required at the endpoint. There is no clock synchronization required between the head end and the endpoint, and there is no signaling protocol required as well. Hence the simplicity of the approach. Consider an example as the one displayed, where I have a segment routing policy that goes from node number 1 to node number 5 via node number 3. So the SR policy head end is node 1. We have a seed list. In this case, that is going to take me to the label or the prefix seed of node 3, and then the label and the prefix seed of node 5. We're going to enable delay measurement underneath the probe, and we're going to enable the so-called measurement mode loopback. On the endpoint, there is no PM configuration required. There is no dependency on the endpoint. All the logic is being applied to the head end only. A little bit more details on what's happening on node 1 is when the probe is configured, the SRPM process will actually craft a packet. The packet will have an IP header where the destination address of the packet is the head end itself. The packet will contain a timestamp provided by the head end. We call that the timestamp number 1. The packet is going to be encapsulated using the same segment routing policy label stack where the PM probe is configured, and the user may have an option to specify the reverse path for how the packets are going to come back. We'll talk more about that in a moment. So as a result, the packet that is going to be built will have the labels that correspond to the SR MPLS policy. The destination address of the IP header is going to be itself node number 1 IP address, 1.1.1, and then underneath we have the actual payload, which is a typical TWAMP UDP packet from RFC 5357. With this encapsulation, the PM packet will be delivered over the network, and it's going to arrive at node 5 without any labels. Both of the labels of the policy have been popped before the packet reaches 5. So now I have an IP packet that arrives on node number 5. At the endpoint, the PM probe packet are going to be simply loop backed. In this case, the packets are coming in with the destination address of 1.1.1, which is my head end. Therefore, the node number 5 is going to do a IP lookup and look at the destination address and send the packet back. As was mentioned before, if the user includes a reverse path label, then the endpoint will simply follow the forwarding entry that corresponds to the reverse path label that was imposed by the head end. And lastly, there is no timestamping performed at the endpoint. So minimal to no requirements at all on the endpoint. So the packet in this case is going to be sent back to the head end. If we see that it has a label, this is the label that corresponds to the destination address. So node number 5, after looking at the IP address of the destination, it actually ends up following a push of the label corresponding to node 1, in this case 16001. The packet is switched by the network with that label, and it arrives at node number 1. At that point, the head end is going to receive the packet, is going to collect what we call timestamp number 4, and that timestamp T4 will be stored in the local point buffer. With T4 and T1, the head end can actually compute a round-trip delay estimation, T4 minus T1, and it can also estimate the one-way delay, dividing that round-trip delay by 2. If we look at some basic configuration examples, we see a manual policy, in this case, policy foo, where we enable performance measurement, we enable delay measurement underneath it, and the configuration of the performance measurement submode, it includes a default SR policy delay profile. And in this very simple example, we're only configuring the measurement mode to be loopback mode. Now, let's actually watch an example of this measurement mode loopback for delay measurement over SR policy. Well, so here we are on a router console, router 99. We're going to see an example of a delay measurement operation over an SR policy using loopback mode. First, we can see our delay profile. This is actually a name profile. We're going to call it sample delay profile. In that delay profile, we specify the measurement mode, loopback, and we also specify the frequency by which we send packets. In this case, we're sending packets at 500 milliseconds, so twice per second, 2 packets per second. This delay profile is actually applied to a manual policy. So here we have a manual policy called sample SR policy 2. We specify the performance measurement. We enable delay measurement over it. We can enable properties like logging, and we apply the delay profile from the previous section, from the previous command. We can see that in this example, I have also specified the reverse path label that I want to follow. So this is going to be an extra label that will be imposed by the SRT head end when we send the PM packet, in addition to the labels of the policy that we are monitoring. Well, here we can see a detail of that policy where we have enabled PM. It happened to have two labels. So we're going to go to node 44 via node 88. And the PM packet will have an extra label of the label of node 99, which is in this case is the source. This explains the flexibility you have to add labels for the reverse path. If you don't specify a label for the reverse path, then the endpoint is just simply going to take a look at the destination IP address of the PM packet, which is going to be the head end itself, as we explained in the previous slides. Well, if we look at the OPER data for that policy, so we're going to look at the performance measurement operational data for the policy that we are monitoring. In this case, we can see the profile that is being applied and the type of profile. So in this case, it's a profile for SR policy for delay measurement. We can see the reverse path label that was configured in this case, and we can actually see the measurements that are being collected. In this particular case, we are sending 2 packets per second over 30 seconds with the default configuration, so that's 60 packets being sent, 60 packets being received, and our measured delay is equal to 11 microseconds. So here you go. Here's a live example of running a delay measurement probe over an SR policy using the measurement mode of loopback, which is going to remove any dependency on the endpoint node itself. We followed to the next topic in SR performance monitoring, and we arrive at what we call SR policy liveness monitoring. It's a very important feature. It is one that allows the operator to verify the forwarding plane integrity of an SR policy. Are my packets making it to the endpoint? Is the data plane set up correctly? Like was the case before, the idea is to provide a simpler deployment at high scale, this time for monitoring liveness over an SR policy path. And like before, we also like to remove any endpoint dependency. The probe packets used for liveness are simply switched back by the endpoint back to the head end. There is no signaling, there is no bootstrapping of a protocol required for the liveness monitoring. There is no BFT being used for the liveness monitoring. We are removing dependency on the protocol. We are simplifying the operation of the probe. Because we're doing liveness monitoring, the head end will have the ability to perform invalidation actions, such as, for example, provide a notification if the data plane is not successful in its verification, or actually bring down the active candidate path of the policy in case there is the detection of the liveness failure. If we use the same example of a policy from node 1 to node 5, this time we enable liveness detection on the policy. We will use the loopback mode again on the liveness probe that is running over the SR policy. Like before, a PM probe packet will be crafted by the head end by using itself as a destination address on the IP packet. We're going to encapsulate the PM packet in the SR policy label stack. We also have the ability to specify any labels that we want to use for the traffic to come back as an optional parameter. So no changes from the previous section where the packet will be crafted and delivered over the network. It arrives as an IP packet, in this particular case, at the endpoint, and the endpoint will do the same as it did last time. It's going to send the packet back based on the IP destination address, or if it's coming with a label, it's going to follow the forwarding entry for the label that the packet is arriving at the endpoint. Nothing else. The packet will come back, in this case, coming back and using the IP return path scenario, the endpoint is just going to push the label of the corresponding to the destination address 1.1.1, which in this case is 16,001. The packet will make it all the way to the head end. When the packet is coming back, the liveness failure detection will be able to make sure that we're not losing these PM liveness packets. And if we lose more than n consecutive prof packets, then we can apply a failure action. So here's an example of a policy manually configured with performance measurement and liveness detection enabled, and then we configure a invalidation action. As I mentioned, if I just want to get notification if the liveness detection fails, or if I want to bring down the operational state of the active candidate path. In this particular case, I do not have a name profile applied, which means that I'm going to use the default SR policy liveness profile, which is configured to use the measurement mode loopback. Here's an example of another policy where I'm actually adding the configuration for the reverse path, so that the PM packets used for liveness will include the labels of the SR policy in addition to the labels specified in the reverse path. Okay, so here we are in a head-end router that has a SR policy, which is running a PM liveness detection probe over it. So we take a look at the, first of all, we take a look at a named SR policy liveness profile. The name of that profile is called sample liveness profile. Here we can specify for liveness detection how many consecutive packets should I lose before I can take an action. In this case, we call it the multiplier of value 5. We will also configure the measurement probe used in the liveness, which is always loopback. And we can configure the transmission rate of the liveness packets. In this case, we're running them at every 500 milliseconds. Here is a policy called the sample SR policy. It's a manual policy enabled for performance measurement, enabled for liveness detection. In the liveness detection, I can assign the profile. So I'm going to call the profile from the previous show command, sample liveness profile, and I'm going to enable other features such as, for example, logging. In this case, I'm not configuring an invalidation action down, but rather I'm enabling logging, so a syslog or an alarm can be raised in case the failure detection condition is raised. So here's my segment routing policy. It's going to go from router number 11, to router 99, and then to router 44, so 2 labels for that SR policy. So here we have the operational data for the operation running over the policy. In this particular case, we can see that the liveness detection is enabled and that the session state is up. If we take a look at the log, here we can see the alarms being raised for the policy that we're monitoring. In this case, we can see the last time that the PM liveness session state changed. In this case, it changed to the up state. So now what I'm going to do is I'm going to trigger a failure. I'm going to go to the tail end of this policy, which is router 44. Okay, so now here we are at the tail end of the policy where I'm going to create a failure by shutting down the loopback that is being used as the last seed of the seed list. That will be interface loopback 1. I'm going to shut it down. Now let me come back to the head end. In the head end, if I look at the log again, we can see that there was an alarm that came just now where we actually declare that the PM liveness session went down for the particular policy in question, so the active candidate path was invalid. We can see now that the operational data for the policy is that the session state is down. Okay, now we're going to move on to our third area of segment routing MPLS innovations for iOS XR 7.3.1, and that is segment routing traffic engineering. We're going to highlight one of the new key functionalities available for SRTE that we call Cumulative-Metric bounds. With this new functionality, we're going to allow an SRTE head end to compute a path based on the optimization objective, which is the main metric of the policy, plus a new cumulative-metric bound. For example, a head end can compute a path that will return the shortest IGP path to an endpoint that also qualifies of not exceeding a cumulative delay. And why is this important? Well, it allows the service provider to offer a multi-tier delay SLA offering, for example. For example, a business traffic may have a delay constraint. it's important to see that not all the traffic needs to have the absolute minimum delay. Some traffic may have a delay constraint that we do not want to exceed. So in the figure, the traffic that needs to go from 1 to 6 may actually minimize the cost, so the cumulative IGP metric, and it may go all the way from the access to the core and come back to the access node number 6. Or if the traffic needs to have the absolute minimum delay between the head end and the tail, it may just go straight from access node 1 to access node 6. But there you have very little capacity. On the other hand, you may have a type of traffic that needs to go from 1 to 6 where you want to minimize the IGP cost, but also have a delay that is not going to exceed an upper bound of, let's say, 15 milliseconds. And that one might take me somewhere in between, represented by the yellow line. So the objective is to be able to improve the network utilization by moving the traffic to where the capacity is, while still being able to maintain, in this case, a delay SLA. Under the configuration of a manual SRTE policy, you will have a new area where you will configure the constraints. The constraints will be of the bound type, cumulative bound to be precise, where you can specify the upper bound that will be used for the policy path computation, whether it is of upper bound of metric type TE with a value, IGP, latency, or hop count. So any of these bound types are available for the computation of the algorithm. In addition to manual SRTE policies, we can also specify cumulative bounds for an on-demand SRTE policy. Remember that the on-demand SRTE policy will be triggered by the parameters specified in the ODN color template, which is what we're showing here. So now the ODN color template has been augmented to include the bounds that apply for policies triggered by this template. A configuration example that is more complete, in this case we have a manual policy where we specify a dynamic path. It's going to be computed by the head end, and that dynamic path will have two key aspects. One, it will try to optimize for the IGP metric, so the IGP becomes what we call the optimization objective. And on the other hand, this path will also have a constraints for cumulative bounds of type latency. So with this example, we're trying to provide an SLA for traffic that will be put into this policy. It's going to minimize the cost with a cumulative delay that will be less than or equal to 55 milliseconds. In the next example, we show an ODN color template for color 20 that will be used for triggering on-demand SR policies. This time, we keep the same optimization objective of metric IGP, but this time we provide a cumulative bound of T metric equal to 60. So the SLA or the transport SLA of traffic matching this policy will be minimize the cost with a cumulative TE value less than or equal to 60. Okay, so here we are on a iOS XR router to demonstrate the cumulative delay bound functionality. This is SRTE head end. We will start demonstration with a policy. It is a manual policy that has a dynamic path. It's just going to try to minimize the cost, basically using the IGP metric as the optimization objective. In this case, the policy is going to go from router number 1 to router number 4. And if we take a look at the policy that is going to be installed into the forwarding, it's a policy that has, in this case, the prefix seed of the destination, so 16,004. The IGP cost over that policy has a value of 20, so that's my cumulative IGP metric. Based on the topology that I have in this network, the delay over this path is actually 22 milliseconds. So 20 for the value of the cumulative IGP metric and 22 for the delay. How do I know it's 22? It's based on the delays that I have installed already in the network, could have been verified, for example, with a delay measurement operation running over the policy. But in this case, we're not using the delay in any form for the path computation. So now we're going to change that, and we're going to configure a cumulative delay bound on this example. So what we have done is to the policy that we have been looking at, we're going to add a constraint bound cumulative of type latency. The upper bound that I'm going to be looking for is something that I know will not meet the default IGP path from the previous outputs. So I mentioned that we have a delay of 22, so I'm going to be asking for 21 milliseconds. So I'm going to commit the configuration, and I'm going to get out. So now I'm going to take a look at the computation of that policy by the head end. So here we have our bound of 21 that we have configured. We can observe now there is going to be a new path, different than the previous one. This path is minimizing for the IGP while still meeting the latency bound. The IGP, cumulative IGP cost has now increased from 20 to 30, and my cumulative latency is 19. So with 19, I meet the bound of 21. We can also see in the output of the show command what is also the cumulative-T metric. The output of the router will provide you that, as well as the cumulative IGP metric 30 that we saw a moment ago. So with this particular SR policy, to meet this criteria of minimum IGP and cumulative delay of less than 21, we have a new path which is encoded in this case as shown in the output. So with that, we demonstrate the new ability for an SRT head end to compute a path based on an optimization objective as well as a cumulative metric bound. So now we're going to continue into the main flow and go to our next topic of innovations.